Mauve, Mendeleev, and Fat Man. Hello. As usual, we're going to review. Then we're going to talk about superstars and their families. We're particularly going to pay attention to maternal mortality rate, which is an important thing for the previous world and not so much for our own. We're going to look at Perkins and Perkins Mauve, a color sensation. We're going to look at Freud and Einstein, and we're going to also look again at paradigms and how they've changed. And then we're going to remind ourselves that for the last two lectures, we're really focusing on the present, but more on the future. Where are we going, and what is the world of the future going to look like, and how is science going to affect it? Now we're just rounding the turn into the 20th century and looking into the 20th and 21st centuries. Now we're thinking about the present and the future. We want to see not only where we've been, but where we're going, and Darwin's challenges, as well as the key ideas from Chapter 5, which include progress, globalization, objectivity, God, evolution, power, and time. All of those will stay with us. Now, in one small way, I'm dissatisfied with our book, in the desire not to write a false narrative saying there were only a few scientific geniuses that carried the rest of us forward, and to remind us that the famous firsts were firsts in hindsight, not at the time, and in the desire to give us a real context and to explain that others who aren't famous were important too. Our author, Patricia Farah, sometimes underplays some of the pretty wonderful things that people actually did. But she's right, context counts, and I want to talk about that. Now, here are three people who did pioneering work in medicine and chemistry, who carried their fields forward into the 20th century. Now, when we see what science does in the services of war, it's not good. But these people, while not perfect, are really worthy of admiration, so I want to tell you their stories. Before we do that, let me give you a little context. And the context I'm choosing, maternal mortality, is not the usual way that we put these stories together, but it's a backdrop for every century up to our own, so I think we should look at it. We're going to begin with John Snow, who had a relatively short life, only 45 years. He was an obstetrician, which in those days was a profession that killed women as well as saving them. And to tell you this part of the story, I'm referring to a rather well-written article for the British Medical Journal Online, which covers the growth and the development of obstetrics, delivering babies. In the 19th and 20th centuries, doctors who performed postmortem exams were unfortunately the vector for puerperal fever, which is a disease that killed healthy pregnant women who were lying-in hospitals. By contrast, the wards in these lying-in areas, which were handled by midwives only, in other words, women who didn't attend postmortem examinations and dissections, those wards were much healthier and had a much lower death rate. But the ones where the doctors visited, they had a much higher death rate. Even so, between these two, the overall average mortality rate for childbirth was 1 in 200 until the 20th century. So, in this context, it's a little bit of a risk to have a kid, maybe more than a little bit of a risk. John Snow worked as an obstetrician during a time when the medical community had developed forceps, and men were beginning to specialize in this field, and when many women had large families, meaning they took this chance of dying repeatedly. And Queen Victoria was no exception. She had 9 children. In 1853, John Snow attended the birth of Queen Victoria's 8th child, Prince Leopold. This is Queen Victoria of England. Snow was a member of the Westminster Medical Society, and he was a speaker and a regular publisher of papers and books. He was a careful observer and a practitioner, and he became recognized as a highly skilled anesthesiologist. Although one might think that this was the most important role that he might play, delivering the heir to a throne using a very new medical practice, he also had an even more important public role, and I'm going to tell you the full story here. So Snow started in the age of 14 in medicine, and he had experience as a young medical apprentice when he was 19 with cholera outbreaks. As he progressed in his career, he continued in discussions with medical colleagues about cholera. London had some truly terrible cholera outbreaks in 1849 and 1854, and at the time no one knew what caused these outbreaks or what cholera was. Here's what we know now. Cholera is caused by the bacterium Vibrio cholerae, which attacks the small intestine. It causes the intestine to flush itself without stopping, which creates severe diarrhea, vomiting, and dehydration. It's horrible, and it's horribly quick. The disease typically runs its course between 2 and 7 days, but it can actually kill within hours. And untreated, it kills about 50% or more of those infected. However, it is almost entirely preventable. With medicine and rehydration and salts, almost everyone lives. So Vibrio cholerae is transmitted by feces getting into the water supply. So chlorination, boiling water, or even storing water in narrow neck jars can all help prevent cholera. Sadly, to the shame of the civilized world, this is still a global scourge, with the last outbreak being after an earthquake in Haiti from 2010 to 2011, which killed about 6,600 people. And I say shame not because an outbreak can happen, but because the treatment is inexpensive and it's pretty easy to ship anywhere. Well, during the 1854 cholera outbreak, John Snow tracked the number of deaths in the houses around the Broad Street pump, and he guessed that it was the water source causing the problems. Now, in Edward Tufte's book Visual and Statistical Thinking, Displays of Evidence for Making Decisions, where this story is told and where this illustration comes from, he said this: Snow detected a link between different water supplies and varying rates of cholera, to the consternation of private water companies who anonymously denounced Snow's work. Snow's work and theory was in opposition to the commonly accepted theory that bad air caused cholera. So the little black lines on the map represent deaths. Rather than looking at when most deaths were happening on a timeline, he used a geographical map that showed where most deaths were happening in space orientation. And so it was around the Broad Street pump, which I've circled, and you can see the little black lines that are heaviest there. There's a workhouse and a brewery in yellow nearby, but the deaths in those two places were much lower because they had their own water supply. So now if you think bad air is causing a problem, you naturally wouldn't think that you can do much about it. If you think bad water is causing a problem, then you look at water sources and perhaps you think that you can do something. Snow wrote, I had an interview with the Board of Guardians of St. James Parish on the evening of Thursday, the 7th of September in 1854, and I represented the above circumstances to them, meaning this business about where he thought the bad water was coming from. In consequence of what I said, the handle of the pump was removed on the following day. And then he wrote a book called On the Mode of Communication of Cholera to tell his story and to present his ideas, and that was in 1855, the year after. Well, unfortunately, Snow died of a stroke at the age of 45. But worse than that, well, maybe not worse for him, but worse generally, the Board of Guardians put the handle of the pump back on because they really weren't convinced by the evidence that Snow had shown them. It wasn't until 11 years later, in 1866, that the bacterium was discovered. Now, Snow's work on cholera is a really good example of a number of elements in science, of experience, intuition, and observation, leading to a later confirmation, a paradigm shift, and of the problems that come when you have to convince the public, who had to change both their habits and their ideas. Well, let's turn to another part of the world, to Siberia, where another woman played the same maternity roulette by having a large family. The mother of Dmitry Mendeleev, Maria, came from a comfortably wealthy family in Tobolsk, which was a city that was an administrative hub for Siberia. Maria didn't get a formal education, but she did love learning. In 1809, she married a man who had an education, Ivan, who came from the Moscow region. He had gotten a degree in St. Petersburg, and he came to Tobolsk in 1807 to teach. By 1828, he became the director of what's called the Tobolsk Gymnasium. It's like a combined junior high and high school for kids who plan to go on to college. Maria and Ivan had a large family together, at least 11 children, of whom 8 made it to adulthood. And the last of their children, born in 1834, was Dmitry. Well, when Ivan was blinded by cataracts, he could no longer work. Maria had to take over the glass factory that was owned by her family, and she got it running. Maria homeschooled Dmitry, and she encouraged him in chemistry and math, which made sense for a glass factory. However, life got pretty hard for the family. Ivan died in 1847, and then the glass factory burned down in 1848. So at that point, Maria decided to take the 15-year-old Dmitri, her shining hope, to Moscow to get an education. She also took her next youngest daughter, Elizabeth, with her. They walked and they rode 1,400 miles, about a month's journey. And when they got to Moscow, the university refused to take Dmitri because he was a student from Tobolsk, and it was outside of their administrative region. So Maria, Dmitri, and Elizabeth continued on to St. Petersburg, another 400 plus miles, which was another week along the way, and they finally were able to enroll him in the school that his father had attended, the Chief Pedagogical Institute in the University of St. Petersburg. And then, in 1850, Maria and her daughter Elizabeth died of tuberculosis, leaving Dmitri at school alone. It's not a very happy tale up to this point, but it is certainly one that points to the power of families. A powerful will to recover from tragedy and a dedication to education really characterized Dmitri Mendeleev's mother. Mendeleev himself got tuberculosis in 1852, but he defied the medical expectations and he didn't die. Instead, he graduated, got to work teaching in Crimea, where he got better, and he went in 1860 to the first International Conference on Chemistry in Karlsruhe, Germany. By the way, he said himself that he wasn't very good at German in school, but later on, as you see, it was important for him to be reasonably good at German, so a reminder to study a foreign language and really learn it. Well, you need to recall that 1859 is the year that Darwin published The Origin of Species, so this is a time of scientific and social ferment in a number of related fields, biology, chemistry, medicine. In 1861, Mendeleev published Organic Chemistry, which is a very welcome addition to that field, and he won the Demidov Prize, which came with 5,000 rubles, which was just enough for a wedding trip in 1862. And then he was appointed the chair of general chemistry at St. Petersburg in 1867. So these were good years for Mendeleev, consolidating and building his knowledge and reputation, settling in. But he wasn't earning a lot of money, and he struggled to get any time to do research. Instead, he did a lot of lecturing to make ends meet. And there is online a highly informed, culturally fascinating, slightly dense account of Mendeleev by Igor Dmitriev, who is the director of the Mendeleev Museum and Archives in St. Petersburg University. And he quotes Mendeleev describing his own story. He says that he was teaching at St. Petersburg, also the Institute of the Corps of Railroad Engineers, and the Nikolaev Engineering Academy, and the college and the 2nd Cadet Corps. So he's working 4 jobs. And he says, running around like mad, I hope I would not ruin myself. But there's also a good thing about it. You learn to present your ideas and see what is missing. That makes a little bit of sense. If he's lecturing in 4 different places and he's kind of trying to keep up with all these different things, he's going to learn how to be efficient at conveying his ideas. He was also something apparently of a showboater and a jokester as a lecturer, but he did want to be engaging and clear, and I do admire that. And also I want to remember that he did have the capacity to communicate in several languages. Well, working like that, you'd find it hard to find time to do research. So Mendeleev had been working on ideas about chemical weights, and he was working on a textbook called Principles of Chemistry, and he had known the chemical weights, and he had put them on a series of cards, and he was reviewing them when he fell asleep at his desk. This is the desk. And this is what he says about that. He said, in a dream, I saw a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. And that's his story about the origin of the periodic table. He's not the first to consign the problem to the subconscious and solve it in a dream. In fact, we're going to get to Freud in a couple of minutes. This discovery is like the others that we've been talking about all throughout this course. There's a period of intense, repeated observation. There's a problem to be solved. The solution is maybe intuitive and the problem follows, or the proof follows. And the discoverer is not really at a desk all by himself. There are a lot of people who came before and around. In this case, quite memorably, Mendeleev's mother. Well, here's the modern version of the periodic table. And Mendeleev was actually not the first to be working on this problem, but he was the first to make a table that worked, that fixed the problems of the elemental weights of the past and predicted atomic weights for the elements that were as yet undiscovered. He was highly recognized. He was honored in the scientific community, but he did divorce and remarry in his 40s, and that was a scandal at the time. And so that second marriage kept him from being elected to the Russian Academy of Sciences. He taught and published and did research for 35 years, and then he retired from the university. Post-retirement, he worked for the Russian government at the Bureau of Weights and Measures, and he also worked on developing the natural petroleum resources of Russia. He died in 1907 of influenza. Science was still a pretty broad field to be in. There wasn't a boundary to say that Mendeleev had to only study chemistry, or that he couldn't work in physics, or he couldn't consider the economy. And he did all of those things and more. He was a chemist of genius, I'm quoting here, a chemist of genius, a first-class physicist, a fruitful researcher in the fields of hydrodynamics, meteorology, geology, certain branches of chemical technology, and other disciplines adjacent to chemistry and physics, a thorough expert of chemical industry and industry in general, and an original thinker in the field of economy. Now let's step back to that question of maternal mortality and consider another leading light in science, Marie Curie. She won 2 Nobel Prizes. How did she get there? Curie was born in the middle of that decade of ferment in 1867 as the youngest of 5. Her parents were teachers who had lost their family fortunes in the political struggles of Poland to resist the partition by Prussia and Russia. By 1878, when she was 10, her mother had died of tuberculosis, and her older sister had earlier died of typhus. Now think of this. Everyone we're looking at this week suffered the loss of a family member from a disease that is no longer a problem for us. Maria and her older sister Bronislawa attended the Flying University from 1885 to 1905. Flying University was a secret underground college that resisted the political agenda of Russia and Germany and, particularly important for Maria and her sister, admitted women. It had upwards of 500 students across its first 20-year experience. Bronislawa left Warsaw for Paris at 19, and Maria financially supported her older sister by working as a governess. Bronislawa focused on gynecology and obstetrics, graduated, and married a doctor in 1890. Then, after some urging and some more saving up, Maria joined Bronislawa in Paris in 1891 when she was 24. She began studying physics at the University of Paris and graduated in 1893. She went on and received a second degree in 1894, and she became known by the French version of her name, Marie. She began working in industry and then met her future husband, Pierre. She wasn't so sure about marriage. She hoped to return to Poland, and she did so briefly. But in the end, she decided that marriage was all right and returned to France and married Pierre in 1895. In 1896, there came the first big breakthrough. The Curies and the French physicist Henri Becquerel together discovered uranium rays. This electrometer was one of the early instruments that she and Pierre used to measure radioactivity. The pan below is attached to a quartz crystal above. Weights hung on the crystal produced a small but steady burst of electrons that they could measure. This phenomenon is called piezoelectricity, and it was discovered by Pierre and his brother Jacques in 1880. Many years later, in 1903, that tool was used to record radiation, for which the Curies and Henri Becquerel received a Nobel Prize in physics. Pierre, unfortunately, was killed in a street accident in 1906. Marie continued her work and received a second Nobel Prize in 1911 in chemistry for the isolation of radium and polonium. In the slide, I have an excerpt from a speech she made for that second Nobel Prize. Curie comments on the new tools she is using to explore the world. She's looking at substances which are invisible to the microscope and weigh nothing on any scale that she has. Instead, she's working with an electrometer. It measures rays, and since rays can't be measured in any of the old ways, she calls her work, somewhat poetically, the chemistry of the imponderable. Here's a little clip of Marie Curie receiving a gold medal of the American College of Radiology, and she speaks French briefly. I've included that in the notes. And you can see that she's listed as a noted woman scientist who helped her husband discover a rare element. While the comments below the clip are interesting in their own right, there are people who want to see her Polish family name so as to preserve her Polish identity, and there are those who are annoyed by the way she's described as her husband's helper, even though she had 2 Nobel Prizes. During World War II, Curie helped create mobile X-ray units which were used for battlefront triage to help see and set broken bones. Still, after more than 100 years, much of Curie's personal effects, including her clothes, furniture, cookbooks, and laboratory notes, are still radioactive, as author Bill Bryson notes in his book, A Short History of Nearly Everything. Regarded as national and scientific treasures, Curie's laboratory notebooks are stored in lead-lined boxes at France's Bibliothèque Nationale in Paris. Well, we spent some time with superstar scientists. Now let's take a little side jog over to industry. The Victorian century was a time for the young. I mentioned that the engineer who ran the train through the second-story station window in Paris was 19. William Henry Perkin was an 18-year-old and the youngest of 7 who was studying at London's Royal College of Chemistry. And here on the right, he's at the tender age of 14 in a photo he took of himself. I think you can kind of see that he's going to be a force. Well, he was given some Easter break homework when he was 19. He was supposed to be looking for a way to make artificial quinine, which treats malaria. And at the time, given how many people died of disease, that was a good assignment. But after a failed experiment, he discovered accidentally that coal tar, aniline, makes an intense purple dye. That accident happened in the right time in the right place. Purple was very hard to produce from nature, but it was in fashion. Here you can see the cloth and dresses dyed with Perkin's Mauve. It was a huge hit. The dye didn't fade, and it was relatively cheap to make. Royalty wore it, and then everyone else had to wear it, and they could afford to wear it. The book The Color Revolution says that Perkin created more than the dye. She writes, "That industry not only brought new paints, new pigments, and new dyes into the world, but it was ultimately responsible for major innovations such as synthetic rubber, fibers such as nylon and polyester, and miracle drugs such as penicillin." She added, "William Henry Perkin was no different than Bill Gates, Steve Jobs, or Jeff Bezos. All these engineers stumbled across an idea when they were young and unrestrained by the traditions that held back their elders, and they were able to create something brand new and revolutionary." And I've included a few more notes on Perkin in the notes for this lecture. Links in the notes for this lecture. So Perkin took out a patent. He persuaded his father and his brothers to come in on a factory. He capitalized on his discovery, got rich, was elected to the Royal Society, was knighted, and had a medical chemistry created in his name, which is all pretty good stuff. So I presented you with 3 pioneers, and I've placed those stories against the backdrop of maternal mortality and of life and death in families. Many of the scientists and the technicians and engineers and industry captains we think of as being somehow singular actually came from or had large families. Snow is a bit of an anomaly in this sense because he didn't marry, but as I said, he was noted in obstetrics and he was an innovator in public health. In addition to the question of family support, we see in the lives of Mendeleev and Curie the scientific community was no longer only the elite. Instead, it was increasingly penetrated by the middle classes or the wealthy working class. And Perkin, for instance, came from a middle strata but became a Sir by the end of his days. Now, our author, Farah, spent some time with Freud and Einstein. She's interested in a number of things. First, their intellectual accomplishments, and second, their cultural background. They were Jews in Europe. And third, their immense recognizability as figures. Indeed, it was easy for me to find pictures of both of them all over the internet. It was hard for me to find ones that were a little different and showed these 2 men in maybe contemplation or in a way that you might not have seen them before. So I especially liked this Freud reading a handwritten manuscript. What's their legacy? Their legacy is essential ideas that we all take for granted today. For Freud, the idea of the subconscious, which we all understand and believe in as a phenomenon of the brain, that's his idea and that's his legacy. Before him, nobody had those terms. After him, everybody understands those terms. For Einstein, it's the theory of relativity, dealing with energy and time and space. And we will return to that theory in a future lecture. But Freud and Einstein are giants in our world, shaping much of what we know or we think we know. And to finish up this week, there are a couple of points from Chapter 6 that I want to pull out. First, to finish up this week, there are a couple of points from Chapter 6 that I want to point out. First, Farah returns to the problem of the paradigm shift as it relates to new instruments of measurement. How do you know you've got it right? She says, what are the right results? This is the same circular problem that keeps cropping up. If you're measuring something new, how can you be sure that your apparatus is working properly? Scientists are often faced with the problem of deciding what to do with a result that contradicts expectations. If they take it seriously, as Crookes did spiritualism, then they run the risk of sabotaging their reputation, or of skewing a numerical average by including a mistake. If they ignore it, their results look more consistent, but Röntgen and Becquerel succeeded precisely by refusing to overlook the unexpected. This is a persistent problem in science, risking your reputation to validate unexpected results. How do you know that strange results deserve attention rather than exclusion? There isn't a direct answer to that question, but strange results or new instruments are a feature of every breakthrough and innovation. Well, I want to look at one more point, and that is time. I want to remind you that we've looked at time from the beginning of the class until now. We looked at Stonehenge, we looked at the Maya, we looked at all the various ways that people have linked time to power. And time has continued to be linked to power at this point. The British are busy colonizing the rest of the world, and because electricity has become an option for people, they've started to link clocks together and to make sure that time is set by a center which sends out the time to the subsidiary points. And Britain kind of won the war of who's going to be in charge here by having a Greenwich Standard Time. Time was delivered to pubs because the Victorians were also concerned that workers show up not drunk to work, and so pubs were supposed to be closed at a particular time. And the pubs taking their time from a centralized space also led to the possibility of having railroads do the same thing. So railroads and pubs started to help us have the idea of standardized time across the world. And that's one of the big things that changed in the Victorian period and is part of our own world. Another thing we might look at is the world at night. This is what our world looks like now. This was not possible in the Victorian period. When electricity began to be something that everyone could access and use, then the world changed fundamentally, and it changed even from the way it looks from space. Well, all this is going on in Europe and in Victorian England, the US was gearing up for and then in the middle of a civil war. And in the middle of the Civil War, the National Academy of Sciences was established in America, in part to help the war effort. So we have the Royal Society and now we have the National Academy of Sciences, and these are two powerhouses for scientific encouragement and furtherance of new discoveries. Progress in science and technology goes hand in hand with war efforts. And to me, the beginning of modern warfare can be marked with the Gatling gun, which was an invention of the Civil War. It allows a continuous stream of bullets to be pumped out across a battlefield. Its inventor, Dr. Richard Gatling, apparently thought it would reduce the size of armies and show the futility of war. Unfortunately, the opposite happened. War continued, and on an unimaginable scale. On the right, you see the explosion caused by Fat Man over Nagasaki in 1945. And with that sober image, we'll end this lecture.